ciliary body, which we know connects to the ciliary muscles. Contraction causes the lens to become more bulbous, relaxation more oblong. Ciliary body also secretes aqueous humor and vitreous humor through the ciliary process, and the iris is continuous to the ciliary body, helps with the opening of the pupils. That's kind of where we're at right now in general eye anatomy. So the last, well, we got a couple other layers to talk about, but the last tunic to talk about is the retina. Wow, I think my brown nose is not pretty good. So the retina is a very thin piece of tissue found immediately on the surface of the posterior of the choroid. Do you guys dissect cow eyes in A&P lab? No? You guys probably haven't started doing the eyeball yet. Well, when you dissect cow eyes, students used to always, well, eye steps used to dissect cow eyes, used to always have trouble finding the retina because it's so thin that it's usually damaged. They'll always think the choroid's the retina, especially with the cow eye because it's all sparkly because of the extra light reflective capability. But in general, it's just a very thin, delicate piece of tissue. That's why the retina can tear so easy, because it's a really thin, delicate tissue. And the importance of the retina is this is actually where you're going to find your photoreceptors. Your photoreceptors are actually responsible for converting that physical light property, or light waves, into some type of chemical signal or chemical message that can be taken to your brain, processed, and then integrated so that you can actually receive an image. Most of you probably know we have two sets of photoreceptors. What are our photoreceptors? Rods and cones. And most of you might know already that your rods, well maybe not, your rods and cones are important for visualizing different types of images. Your rods are very sensitive. Very sensitive to all light wavelengths. So in case you've never had any type of physics or intro biology in the past that's ever talked about light waves, what is the wavelength of light? And if you think of light, let me use green. So light travels in waves, right? Now the wavelength of light is basically the distance between waves. The intensity of light is going to be more amplitude, right? So wavelength, we have our amplitude. The amplitude is really going to be your intensity of light. What's the wavelength confer to light? Wavelength confers the color of light, okay? So if rods are very sensitive to all light wavelengths, do you think they're going to be very good at distinguishing different colors of light? No, they pretty much just respond to any light, and they pretty much just give the same signal. So these rods are important for black and white low light vision, because they respond, they're very sensitive, and they respond to any type of wavelength of light, okay? But they don't, they basically don't choose what wavelength to respond to though, so they're always going to produce the same type of color energy. Cones, on the other hand, are much more complicated. There's actually 3 types of cones that are important for visualizing different light colors. You can read over them in your review PowerPoint over class. But cones are sensitive to different wavelengths of light, depending on the type of cone. There's 3 different types of cones, each sensitive to a different wavelength. Okay? So basically, these cones are going to be important in differentiating colors, or differentiating light of different wavelengths. So cones, though, are not as sensitive. So they're better for color bright light conditions. All right. Now, another thing about cones is they also innervate with the nervous system a little bit different than rods. And they can actually provide you a higher resolution. They actually can provide you a higher resolution of vision. The resolution is basically just the apparent distance you can observe between 2 points. So the higher the resolution, the lower the actual numerical value of resolution you can see. So if you could resolve something at 1 micron, it would mean that you could distinguish 1 micron between 2 points. None of you can distinguish 1 micron between 2 points. And that would be very high resolution vision. So cones are better for this high resolution vision. And I'll show you that here in a minute when we go over retinal anatomy in general. Because retinal anatomy is going to be highly dependent in function on these rods and cones, because these are your actual photoreceptors that convert light into some type of chemical signal. All right? So let's go over the anatomy of the retina. Okay, so we can draw some rods. Here's a rod. We're not going to get real precise on what a rod looks like right now. We'll draw a cone. Here's a cone. We'll draw multiple ones just for fun. We'll draw another cone up here. All right. Rods and cones are actually found at the most posterior portion of the retina. So the retina is pretty complicated because, like our different tunic layers, you know, our vascular tunic and our fibrous tunic, the retina itself is divided into 3 distinct layers. And the retina layers are going to be the actual photoreceptors, or those rods and cones. A special type of nervous cell that you pretty much only find in the eye. If you remember all the way back to A&P2, we went over neuron anatomy. You might have remembered the 3 different types of neurons. We have multipolar neurons, which we pretty much only talk about in A&P1. We have bipolar neurons, and we have unipolar neurons. Bipolar neurons are very rare. They're pretty much only found in the eyeball. And they make up an entire layer of the eye, or of the retina. Bipolar neurons, so basically some upstream neurons associated with the afferent nervous system, or the afferent neurons leading a signal back to the brain. And then we have some other types of neurons that we call the ganglia layer. These are mostly multipolar neurons, ones that you're kind of familiar with already. All right? Now, the way I've provided you these 3 different layers of the retina, this is going from posterior to anterior. All right? From posterior to anterior. So let's bring our big eye model back down for 1 second. I'll push it back up in a second. So posterior, let's draw a little arrow. Here's our retinal layer. Posterior would be over here. Anterior would be over here. So basically, your rods and cones are going to be abutting that choroid, whereas the upstream afferent neurons are going to be more anterior, abutting that big posterior chamber of the eye. All right? So rods and cones innervate with bipolar cells. If you remember talking about earlier, we're going to go over this again in detail. These rods and cones generally represent what we call separate cells. So these are those cells that produce receptor potentials. And they produce receptor potentials based on light activation. And we'll talk all about how that happens as we get there. Now, these bipolar neurons, if you remember what a bipolar neuron looks like, and don't worry if you don't, I'm going to draw one. My markers have died on me so fast, and they're like brand new. Yeah, there we go. Bipolar neurons are called bipolar neurons because they have a common dendrite that might branch further away from the common dendrite, which is connected to the cell body of the bipolar neuron, which is connected to the axon in the terminal buds. So we have axon, dendrite, we have terminal buds, we have cell body. They're called bipolar because they only have two projections leading away from the cell body, right? So two projections leading away from the cell body. An axon and a dendrite, even though this dendrite can branch more upstream, downstream, whichever you want to call it. You can draw a little nucleus there too, so you know this nucleus. So that's what the bipolar neurons look like. Each cone, this is important. Each cone only innervates one bipolar neuron, right? Each cone innervates one bipolar neuron. That's important. And the reason that's important is because that's what actually gives cones the better ability to recognize high resolution vision, or recognize tinier spaces between two points. Basically because each little cone that's stimulated sends its own signal to the brain via one bipolar neuron. Okay? So only one cone is going to send one signal via a bipolar neuron, which is only going to send one signal to a discrete area in the brain that can then formulate an image through processing and integration. Cones are different. Cones can innervate multiple bipolar neurons. So cones innervate multiple bipolar neurons. What's that? Rods, right? Rods. Rods innervate multiple bipolar neurons. All right? So they send. This is one of the reasons that they can be more sensitive to light, because any amount of light that hits one is going to send multiple signals to the brain to produce an image. However, because multiple images are being sent to the brain at one time, you're losing resolution. And this is kind of equivalent to motor units in muscles. If you think back to A&P2, so a small motor unit will have one neuron per muscle fiber, which gives you a higher resolution control in that muscle group, because you have independent neuronal control of each individual muscle fiber. Whereas a larger motor unit is going to have one motor neuron innervating multiple muscle fibers. So one activation or action potential sent down a motor neuron will cause multiple muscle fibers to contract. So you lose resolution in that muscle fiber, or in that muscle group.